So how far can you push this? So you keep on increasing the dimension, you keep on increasing it further and further and further. What is the limit? What is the limiting case? When do you have to stop? When can't you go any further?
As the dimensions increase, the nodes in each dimension decrease. So what is the limiting case? Eventually, you can only have 2 nodes in each dimension. So if you have p nodes, they will be arranged as 2 cross 2 cross 2 and so on, with 2 nodes in each dimension. Now there are d dimensions. So what is d? Well, 2 to the power d is equal to p. So d must be log p. This is called the hypercube. So what does a hypercube look like? This is what the hypercube looks like in 3 dimensions. And you can visualize how it will look like in higher dimensions.
So let's study the hypercube. So what is the degree? Degree is straightforward, right? Log p. Yeah. Number of links. This is also straightforward. Each node has log p links. There are p nodes, so p log p. There's no point in having a torus, right? In both directions, you'll connect it to the same node. Okay, what is the diameter?
Log p by 2.
Along each dimension, either you have to make a jump or you don't have to make a jump. To reach from any node to any other node, you look at every dimension. Either it's in your dimension or it's not in your dimension. If it's in your dimension, you jump across the link to the other side. Along that dimension, you make a jump, right? And if along that dimension, the destination is not different, if it's on the same side, then you don't make the jump, right? So how many hops will you have to take at most? Log p hops. And there's no log p by 2 here, right? There's no torus concept over here. So diameter is log p, and finally what is the bisection width? Well, there are log p dimensions. The number of links in each dimension is the same, right? What is the total number of links? P log p, yeah, and there are log p dimensions. It's a symmetric network, so the number of links along each dimension is the same. So there must be p links on the bisection width, yeah. Let's look at it another way. This is how you build these architectures also, right? So there is an interesting property that a hypercube has. So the way the numbering is done, numbering I mean the rank numbers or IDs of the nodes, right? Typically the way we view it to build algorithms and to solve problems, the way we number the nodes is as follows. Every node has a number, and how many bits are there in the number? There are log p bits in the number, right? Because there are p nodes and all. So you only need log p bits to represent the ID of a node. So if a node is 1010, right, that's the ID of a node. How many nodes is it connected to? It's connected to log p nodes. In this case, it will be connected to 4 nodes, right? The 4 nodes it is connected to are the nodes which differ from it in exactly 1 bit. Okay, so the node 1010 will be connected to the nodes 1011, 1000, 1110 and 0010. Is that clear? Only the first bit has changed, only the second bit has changed, only the third bit has changed, only the fourth bit has changed from the ID of the original node, from the ID of this node. Yeah? So that's an interesting property that you can build for hypercubes. Okay? So if I give you a complex hypercube, how are you going to give it IDs, right? Where are you going to start from? What are you going to number 0? What are you going to number 1, 2, 3, 4 and so on, so that this property is satisfied, right? So there's a very, very easy way to do it, and let's look at that. It's a simple replicating mechanism. So you start with ID 01. So this is 2 nodes. Now we are going to increase it to 4 nodes. I'm going to replicate this structure. Yeah. I'm going to connect the nodes of the same index, and now I'm going to just append a 0 over here and a 1 over here. As simple as that. If I keep on doing this, I'm going to get a hypercube which satisfies this numbering property that I spoke about. Okay, let's see it one more step. It's quite interesting. So if I want to replicate this, what am I going to do? I'm going to replicate this whole thing 0 1 0 0 1 0 1 1, right? Now I'm going to connect up 0 0 with 0 0, 0 1 with 0 1, 1 1 with 1 1, and 1 0 with 1 0. And now what am I going to do? Well, to the original one I'm going to append a 0, prefix a 0, and to the new one I'm going to prefix a 1. Just look at it. Let's pick up any node. Let's pick up 0 1 1, right? What are the neighbors of 0 1 1? 0 0 1 differs in the second bit, 0 1 with 0 differs in the third bit, and 1 1 1 differs in the first bit. Yeah? So just think about it, because every time you replicate and you connect it up, it's going to differ in that last bit. All the previous bits you already had in the previous network, right? And every time you replicate it and you connect it up, you're going to have another neighbor which differs in the last bit from the right, first bit from the left. Okay? So that's a hypercube. Let's come back to diameter. Diameter we said was log p, and it's obvious why, because every time you take a hop you change one bit, right? So if you are given a source and a destination, which is the furthest node from any node? If I give you a node with ID I, which is the node which is the furthest from this? I complement, right? With all the bits inverted, because then you have to traverse along each dimension to reach that. Yeah? So the furthest from this will be I complement, well, however you want to denote it, yeah. Okay, the other is bisection width. Let's look at bisection width from this construction, right? So how did we build this network? So initially we started with 2 nodes. So every time I add a new dimension, how many new links do I add? So when I'm going from 2 to 4 nodes, I add 2 links. Now when I'm going from 4 to 8 nodes, how many links do I add? 4 links, right? The new links I added is nothing but the bisection width. It divides the network into 2 equal halves because I just replicated half the network. Yeah? So the number of links that I added in the last step is actually the bisection width, and that is nothing but, if the total number of nodes is p, that is p by 2, right? Okay. So that means bisection width should have been p by 2. So what did we do wrong? Let's come back to how we calculated it, right? We said there are p log p links in all. Why did we say there are p log p links? So we said every node has log p edges, so the total number of edges is p log p, but that's between 2 nodes, so you have to divide by 2, right? So total number of links is p log p by 2, and therefore this is actually p log p by 2 divided by log p, which is p by 2, right? And that matches the bisection width, p by 2. Okay? Clear? So let's capture this here, right? I'm going to erase this part to make some space. So number of links, p log p by 2, diameter is log p, bisection width p by 2, and degree log p. Yeah? So if you look at it, it's not bad, right? It looks like quite a good network. A number of links, p log p by 2. If p is not too large, log p is okay, right? But when you're talking about hundred thousands of nodes, then log p starts to become large, okay? Degree log p, again, when you go to hundred thousands of nodes, that becomes slightly unhandleable. Diameter log p, not bad at all. Bisection width p by 2, great, okay? So that's the hypercube. Again, in practice, you don't build hypercubes. The connectivity is not easy to build, okay?